Good morning. Today I am going to explain steady state forced convection heat transfer in laminar flow in a circular tube. So this is the schematic of the problem actually. So what you have here, a cylinder here. So inside of that a fluid is entering at temperature T1, and this is the direction of jet here. So jet direction is along the axis of the cylinder, so the flow is going in jet directions. Now in that only the convection heat transfer will take place from here, that in this direction of the flow. Now in radial direction there would be a conduction part also here, and this wall of the cylinder is maintained at constant heat flux, and this is maintained at some temperature. Due to that, the conduction heat transfer will take place in the radial directions, which will provide the heat to the fluid, and convection will be taking place into the jet direction here. So this is what we have here. So now we can calculate for this. So this is velocity expression from momentum balance in jet direction. So this is from velocity expression from that. So this is delta P R square 4 mu L 1 minus R square upon R square. So here, so if you say that heat is transported into R and Z direction only, so here this calculations from here onwards is just to get the energy flux actually, or you can say energy transport equations, which can be given in the appendix, but this is given from here also, so we can calculate. So total energy at R would be energy vector at R multiplied by this area, energy flux. So you have this, so you can write here 2 pi R ER at R multiplied by Z. Now total energy out at R plus delta R would be equal to 2 pi R ER at R plus delta R into delta Z. Now total energy in at Z, so Ez into 2 pi R into delta R. So this is energy in, so this flux multiplied by area. Energy out, again the flux into area. So flux at Z equal to Z plus delta Z. So multiplied by 2 pi R into delta R. Now work done on the fluid by the gravity. Practically you are calculating mgh upon time. So this part will give you the volume, 2 pi R dr into dz will give you the volume, multiplied by density will give you the mass, multiply by this actually this G will give you energy, and then energy per unit time would be rate of work done actually. Work done is energy actually. Now total energy terms would be 0. So total energy in, out, so in at R, out at R plus delta R, in at Z and out Z plus delta Z, and by the gravity work done on the fluid by gravity. So I substituting all of them here and equating at 0, so we will end up with this one. Now dividing this equation by 2 pi R delta Z, so we will end up here. Now here taking the limit, delta R tends to 0, delta Z tends to 0. So from here we will get this equation. Now again dividing it by R, we will get this minus 1 upon R del R ER upon del R minus del Ez upon del Z plus rho Bz into Gz equal to 0. This is equation 1. Now if we see the total energy flux is actually your that kinetic energy plus here you have here the enthalpy. So enthalpy per unit actually this volume part here multiply by this velocity vector, so it will give you the energy flux. This is again this viscous heating part here. Then this is Q, the Q by conduction actually. So from but for this is given for enthalpy expression H cap minus H cap naught T naught upon T naught to T actually Cp cap dt plus P naught to P V cap minus T del V cap over del T at constant pressure into P. So this is actually expression for enthalpy change for any gas from thermodynamics. For ideal gas actually the volume change is 0. So at here, so this term would be cancelled. So ideal gas actually the enthalpy is given by Cp dt only. Now the non-zero component of B is only in Z direction, so we have the Vz is only non-zero, rest are 0 only, so no velocity in Vr and V theta directions. So your Er term would be tau Rz Bz plus Qr. So this is viscous heating, this one is by conduction heating. So now we can substitute the expression for tau Rz. So this is minus del Vz upon del R into Vz minus K del T upon del R. Now you will end up with this one, you multiplying by R, Er equal to this. So above equation multiplied by R. Now you are taking the derivative of that del upon del R, R, Er. So you are differentiating this term. So first this term you have considered one term, so you are differentiating it first, then differentiating second term, then this one, the whole is being considered at one term. So by doing that you are getting here minus mu Vz del upon del R, R del Vz upon del R minus mu R del Vz upon del R square minus del upon del R Kr del Vz upon del R. Now dividing this equation by 1 upon R, so by 1 upon R you divided our equation by this, so you are ending up here minus Vz mu del upon 1 upon R del upon del R, R del Vz upon del R minus mu del Vz upon del R square minus 1 upon R del upon del R Kr del T upon del R. This is equation number 2. Now Ez you already have that, so Ez equal to 1 upon 2 rho V square plus rho H cap Bz tau Zz Bz plus Qz. So you can substitute expression for here. So you have this tau Zz minus mu del Vz upon del R Vz, and this is minus K del T upon del Z. Now H cap minus H naught cap is given by this from thermodynamics, and this term is getting cancelled, so finally you will end up here Cp cap T minus T naught plus B cap P minus P naught. So from here you will get expression of H cap equal to H naught cap Cp cap T minus T naught plus B cap P minus P naught. So you can multiply it by rho, you will end up with this one. Therefore you can call Ez cap equal to, you have this Ez energy vector in Z direction 1 upon 2 rho V square Vz rho H cap Vz plus Cp cap T minus T naught Vz plus rho V cap P minus P naught into Vz minus 2 mu del Vz upon del R Vz minus k del T upon del Z. You can differentiate this del Ez upon del Z. So if you differentiate that, because this Vz is not the function of Z for fully developed flow, so this term would be 0. This term would also be 0. Here this del T upon del Z term there, so this one again del P upon del Z, and again this term is 0 here because del Vz upon del Z is equal to 0. Now second term is this. So from here, by arranging this, you will get this rho Cp cap Bz del T upon del Z plus Bz del P upon del Z minus k del square T upon del Z square. Now from equation 1 and 3, by substituting all term here, so you substitute every term there. By putting here, you are getting these equations. Now from here you can calculate the expression for rho Cp cap Bz del P upon del Z equal to this 1 upon R del upon del R Kr del T upon del R plus k del square T upon del Z square plus mu del Vz upon del R square plus Vz minus del P upon del Z plus rho gz plus mu 1 upon R del upon del R del Vz upon del R. So this equation actually we can get also from your energy transport equations given in the appendix. So what we derived here, so you can understand how to derive it. Now we will do the Z momentum balance. So if you do the Z momentum balance here, so you have del Vz upon del T plus Vr del Vz upon del R plus del V theta upon del V theta upon R del Vz upon del theta plus Bz del Vz upon del Z equal to minus del P upon del Z plus rho Gz plus 1 upon R del upon del R tau Rz plus 1 upon R del tau theta z upon del theta plus del tau zz upon del z. So this is Z momentum balance, so in cylindrical coordinate. Now from here the several term we can put over the limitations of the problems. First we are solving it steady state of operations, so this term would be cancelled, nothing would change with respect to time. Totally one-dimensional flow only in Z directions, so Vr equal to 0, V theta equal to 0. Now we are talking fully developed flow in Z directions, so del Vz upon del Z would also be equal to 0. Second, we are considering axis symmetric flow, so nothing would change with respect to theta also, so this term del theta Z upon del theta is equal to 0. Again fully developed flow, so del tau zz upon del z is also equal to 0. So by solving it, we are ending up with this equation 0 equal to minus del p upon del z plus rho gz plus mu 1 upon R del upon del R del bz upon del R equal to 0. This is equation 5. So this can be substituted into equation 4. Equation 4 is this one. So your ultimately this whole term will get equal to 0. So your resultant equations would be now this one. With the help of equation 4 and 5, you are getting this equation here. So this equation, so this now we are putting further constraint here, neglecting the viscous heating. So if we neglect viscous heating here, so this term is getting cancelled. Mu del Vz upon del R square equal to 0. Now conduction in axial directions, we are again neglecting here because There you have direction of flow, so the maximum heat would be transferred by convection would be many times higher as compared to the conduction actually. So therefore, by comparative analysis here, we are neglecting this term here. Now therefore, our resultant equations, energy transport equation, will need to be solved. Is this one, rho Cp cap Vz del T upon del Z equal to K 1 upon R del upon del R del T upon del R. And for here Vz equal to Vz max 1 minus R square upon R square for laminar flow. Now substituting this into this one, so this is what is our resultant equations in the rho Cp cap Bz max 1 minus R square upon R square del T upon del Z equal to K 1 upon R del upon del R del T upon del R, equation number 7. So this is the main equation which is need to be solved. Now what boundary conditions we have? First boundary condition, that R equal to 0, T equal to finite, means at the center of the tube you should have a finite temperature. That's fine. Now at R equal to R means you are at the tube wall, so there you have conduction flux would be equal to your here, that total flux which you are maintaining at wall. So wall you are maintaining at constant heat flux, that is Q naught. So the conduction flux will be equal to flux at the wall here at a steady state. At Z equal to 0, the point where the fluid is just entering, so fluid have temperature equal to T1. Now we can non-dimensionalize in non-dimensionalized form that non-dimensionalized temperature. So theta equal to T minus T1 Q naught R upon K. Non-dimensional radius epsilon is being considered R upon R. Non-dimensional distance consider as eta equal to Z rho Cp cap Bz max R square upon K. Now we can differentiate this. Del theta upon del T is this one, that Q naught R upon K. Then from here next one we can find del eta upon del Z would be equal to rho Cp cap Bz max R square upon K. So you will get expression for here del eta. Now from equation 8 and 9 we can write this one, that del theta upon del eta will be equal to rho Cp cap Bz max R square upon K Q naught R upon K multiplied by del T upon del Z. So this we can rearrange it into this particular format, that del T upon del Z would be equal to Q naught R upon K rho Cp cap Vz max R square upon K del theta upon del eta. This is equation number 10. Now del epsilon would be equal to 1 upon R into del R. So now from equation 8 and 11, if you say that, so you will find from here del theta upon del psi equal to 1 upon Q naught R upon K. Then you have here del T upon 1 upon R del R. So from here we will get expression of del T upon del R equal to Q naught R Q naught upon K del theta upon del psi multiplied by R. You will get this term. Differentiate it again with respect to R. You will end up with this R Q naught upon R into K del upon del epsilon del theta upon del epsilon. Now further multiplying it by 1 upon R, you will get this term here. So here you have substituted the expression for R only, so R is epsilon R. Now from equation 7, 8, 9, 10, 11 and 12 you will end up with this particular equation here. So you have rho, this is our equation which will need to be solved, that rho Cp cap Bz max 1 minus epsilon square Q naught R upon K rho Cp cap Vz max R square upon K del theta upon del eta equal to K Q naught upon epsilon R into K del upon del epsilon epsilon del theta upon del epsilon. So by simplifying this you are ending up with this equation 1 minus epsilon square del theta upon del eta equal to 1 upon epsilon del upon del epsilon epsilon del theta upon del epsilon is equation number 13. What boundary condition we have for that? At epsilon equal to 0 means at R equal to 0 we have considered temperature is finite and non-dimensional temperature is T minus T1 Q naught R upon K. So okay, that is some finite value. Second boundary condition at wall, that R equal to capital R, so epsilon would be R upon R would be 1. So this is from here. So then you have del theta upon del epsilon is equal to K upon Q naught del T upon del R. So from here you can just substitute here, so you will get this at R would be Q naught upon K, and finally you are ending up with this answer here 1. Now at eta equal to 0 means at z equal to 0, so eta is z upon so the eta, that t equal to 1, so theta equal to t1 minus t1 upon q naught r upon k equal to 0. So that is at z equal to 0. Now for this, we have something here for large value of eta, after the fluid is sufficiently far downstream from the beginning of the heated section, it is expected that the constant heat flux the wall will result in a rise of the fluid temperature that is linear in eta. It is also expected that the shape of temperature profile is a function of epsilon will ultimately not undergo further change with increasing eta. Hence we should have a asymptotic solution. So your theta expression would be have two functions. One is a purely a function of eta, other one is function of purely of epsilon. Means after a particular time your temperature profile should not change with respect to change in position, so that is eta. Okay, so this function is not complete solution because it doesn't satisfy your boundary condition 3. Now third boundary conditions we are the replacing is by actually integral boundary condition here. So what we are considering here, so this is actually, you can say that your entire tube. So at z equal to 0, what you have here, no energy enters here since datum temperature was chosen here, that T equal to T1. So no energy enters here. Now heating is being done by some means of coil, so that you are maintaining this particular tube all the time at constant flux at Q naught. So this is what is total energy will transfer to the pipe 2 pi Rz into Q naught. Now this particular fluid, when it will leave at section Z here, so energy leaving with here this one, the rho Cp T minus T1 Vz into dr. So this is the energy leaving. So now this is what we are calculating here. So total energy here transfer to the fluid is being balanced by total energy leaving with the fluid, because no energy is being entering with the fluid is in the beginning. So whatever is being given is being taken by the fluid at the exit only. So that's what you have here, 0 to 2 pi, 0 to r. This is rho Cp cap T minus T1 Vz r dr into d phi. So our boundary condition in dimensionless, so we can put dimensionless parameters now. The epsilon is r upon r. You have expression of d epsilon. Theta is T minus T1 Q naught r upon k. So you will get T minus T1 is equal to theta Q naught r upon k. Then Vz equal to Vz max 1 minus r square upon r square. So Vz equal to Vz max 1 minus epsilon square. Now substituting expression of r, t minus t and Vz in boundary condition 4. So we will end up with this equation here, the z rho Cp cap Vz max r square upon r equal to 0 to r theta 1 minus epsilon square into epsilon into d epsilon. So this entire expression is expression of eta. This is the non-dimensional actually distance. So eta equal to 0 to 1 theta 1 minus epsilon square into epsilon d epsilon. This is boundary condition 4. So what I say, that energy entering through the wall over a distance eta is the same as the difference between energy leaving through the cross section at eta and entering at eta equal to 0. Now we have the expression of theta is equal to C0 into eta plus a function of psi, which is a function plus epsilon, which is psi, which is a function of epsilon only. Now we have expression of del theta upon del eta equal to C naught. We can differentiate this. And now del theta upon del epsilon will be equal to del psi upon del epsilon. Now from equation number 13 and 17, so we can calculate from 13 is minus 1 epsilon square C naught 1 minus epsilon del upon del epsilon epsilon del psi upon del epsilon. Now psi is the function of epsilon only, so this partial derivative would be converted to total derivative here. So in that case 1 minus epsilon square C naught equal to 1 upon epsilon d upon d epsilon epsilon d psi upon d epsilon. So this we can rearrange it, and we can rearrange it. So if we rearrange and integrate it once, we will end up with epsilon d psi upon d epsilon equal to epsilon square upon 2 minus epsilon 4 upon 4 bracket close multiply by C naught plus C1. Again integrating it, so you will get d psi upon d epsilon equal to epsilon by 2 minus epsilon cube upon 4 C naught plus C1 upon epsilon. Now again integrating it, you will get this one. Now from equation number 14 and 18 we are getting theta equal to C naught eta plus epsilon square upon 4 minus epsilon 4 upon 16 C naught plus C1 ln epsilon plus C2. Now we have boundary condition 1 at epsilon equal to 0 theta must be a finite. So if I put epsilon equal to 0, this term is becoming infinite. So it means that to make it finite, that constant C1 must be equal to 0. So therefore C1 is 0 to make this finite. So now boundary condition 2, that epsilon equal to 1 del theta upon del epsilon equal to 1. So from equation number 19, you can differentiate it here. So if you differentiate here, you will get del theta upon del epsilon equal to 2 epsilon upon 4 minus 4 epsilon cube upon 16 into C naught plus C1 upon epsilon. So we have already proved that C1 equal to 0. So if you put that, so from here you will get constant C0 equal to 4. Now your theta expression is this one by putting the value of constant C0. So theta is 4 eta plus 4 epsilon square upon 4 minus epsilon 4 upon 16 plus C2. Now what boundary condition 4 is? Eta equal to 0 to 1 theta 1 minus epsilon square into epsilon into d epsilon. So now substitute expression for theta. So eta is this 0 to 1 4 eta plus epsilon square minus epsilon 4 upon 4 plus C2. Then you have 1 minus epsilon square into epsilon into d epsilon. So multiply it and open the bracket. So if you multiply, open the bracket, you will end up with this 4 eta epsilon minus epsilon cube plus epsilon cube minus epsilon 5 minus epsilon 5 upon 4 plus epsilon 7 upon 4 plus C2 epsilon minus epsilon cube into d epsilon. So integrate it and substitute the limit. So if you will integrate it, substitute the limit here. So you will end up with this, that eta equal to, finally you will end up with this one, eta equal to eta plus 14 upon 4 into 6 into 8 plus C2 by 4. From here C2 is coming out to be minus 7 upon 24. Now we have expression for C2 now, so we can substitute here. The final expression of theta is 4 eta plus epsilon square upon 4 minus epsilon 4 upon 16 into 4 minus 7 upon 14. From here you will end up with your expression of theta is 4 eta plus epsilon square minus epsilon 4 upon 4 minus 7 upon 40. It is exact in limit as eta tends to infinity. For eta greater than 0.1, it predicts the local value of theta to be within about 2%. Now average temperature of the fluid, so that is arithmetic average over the cross sections. So this is expression of temperature multiplied by area R dr d phi, integrated over the entire area divided by area of cross section here. So that is called arithmetic average temperature. So you have that expression of theta, that 4 eta epsilon square minus epsilon 4 upon 4 minus 7 upon 24. So you can substitute that theta is t minus t1 q naught r upon k equal to 4 eta plus epsilon square minus epsilon 4 upon 4 minus 7 upon 14. So from here you will get expression of t is this one. Then you have epsilon is r upon r. From here you will get r equal to epsilon r. So you will get dr equal to r d epsilon. Now we can substitute that expression there. You will get 2 pi 0 to 1 t1 4 eta plus epsilon square minus epsilon 4 upon 4 minus 7 upon 24 q naught r upon k multiply epsilon r into r d epsilon. So you can integrate it, so multiply it and integrate it. So if you are doing that, so you'll get here this equation here, that 2 pi r square t1 upon 2 plus 4 eta 1 by 2 plus 12 minus 2 minus 7 upon 48 q naught r upon k. So from here you got 2 pi r square t1 upon 2, 4 eta by 2, 3 by 48 q naught r upon k. Area is 0 to 2 pi, 0 to r dr d phi is 2 pi r square upon r is pi r square. Now the average arithmetic temperature is this, the divided by this, so from here you will get T average arithmetic is equal T1 plus 4 eta plus 1 upon 8 q naught r upon k. Now the bulk temperature TB is being calculated by this velocity into T average, so and then divide by average velocity is called the bulk temperatures. So in that case you are getting Vz T R into d phi divided by 0 to divided by this actually volumetric flow rate. So for that 0 to 2 pi, 0 to r, Vz r dr d phi. So for that you have expression for Vz is Vz max 1 minus r square upon r is given in non-dimensional term, Vz max 1 minus epsilon square. Now you have this one, that the numerator term 0 to 2 pi, 0 to r, Vz r dr d phi equal to this 2 pi 0 to 1 Vz max 1 minus epsilon square, and then we have expression of T, actually this one is T1 plus 4 eta plus epsilon square minus epsilon 4 upon 4 minus 7 by 24 q naught r upon k multiply r epsilon r, then dr r d epsilon, and d phi is already integrated here. So from here multiply it. So if you will multiply it carefully, so you will multiply here, so you will end up with 2 pi r square Vz max, multiply and integrate that T1 epsilon square by 2 minus epsilon 4 upon 4 plus 4 eta epsilon square upon 2 minus epsilon 4 upon 4 plus epsilon 4 upon 4 minus epsilon 6 upon 6 minus 1 by 4 epsilon 6 upon 6 minus epsilon 8 upon 8 minus 7 by 24 epsilon square upon 2 minus epsilon 4 upon 4 bracket close multiplied by q naught r upon k. Then you substitute the limit there 0 to 1. So you substitute here, then if you solve it carefully, so if you solve it carefully you will end up with this one, 2 pi r square Vz max T1 upon 4, then this is q naught r upon k, so into eta. So this you have, so now you have this one, that Vz r dr d phi. So if you integrate that here with respect to r and phi, you will end up there 2 pi r Vz max r square upon 4. Substituting every term back from equation 26, 27 and 28, you get Tb, the bulk temperature is 2 pi r square Vz max T1 upon 4 plus 4 pi 4 eta upon 4 q naught upon r upon 2 pi r square Vz max 1 by 4. So you are getting bulk temperature is Tb equal to T1 plus 4 eta q naught upon r. So the T bulk would be obtained if the tube were choked off at Z and if fluid issuing forth were collected in a container and thoroughly mixed. This average temperature is sometimes referred to as a cup mix temperature or flow average temperature. Now from equation 22 you have temperature expression T is T1 plus 4 eta epsilon square minus epsilon 4 upon 4 minus 7 upon 24 Q naught upon R. You have wall temperature expressions, so at wall temperature you have this epsilon is 1, so substitute that. So from here wall temperature is T1 plus 4 eta plus 11 by 24 Q naught R upon K. So now from here you can calculate TW T wall minus T bulk, so that would be there. You have T wall expression from here, bulk expression temperature you have just derived, so you have this one. Now from here you are getting 11 upon 24 Q naught R upon K. Now from here we will get 11 upon 48 Q naught D upon R, Q naught D upon K. Now Q naught is H TW minus TB for convections. Now from here we can have from the previous one we can substitute expression of TW minus TB, so you have here Q naught upon H. So from here you have HD upon K equal to 48 upon 11. So the Nusselt number equal to 48 and upon 11 for laminar flow through tubes based on wall and bulk temperature. Now we can calculate centerline temperature at epsilon equal to 0 or R equal to 0. So T0 equal to T1 4 eta plus this 4 eta minus 7 by 24 Q naught R upon K. Now based on that we can calculate TW minus T naught equal to this one, that 3 upon 4 Q naught R upon K. Then we can convert R into diameter, 3 upon 8 Q naught D upon K. Again we can equate this from convection flux equal to Q naught equal to H TW minus T naught. So based on that you will get Q naught upon H equal to 3 by 8 Q naught D upon K. So from here you will get Nusselt number HD upon K would be 8 by 3. So this is the Nusselt number for laminar flow based on the wall and centerline temperature. Nusselt number based on wall and bulk temperature is 48 upon 11. So these are all necessary derivations for this convection force flow in fully developed flow in a tube for constant flux at the wall. Reference is Stewart Lightfoot, the transport phenomena. That in case of any doubts and suggestions you can drop it. Thank you very much.